Velcro.
Kevlar.
Gecko tape.
Where does all this stuff come from?
Well, Velcro was inspired by the tiny little hooks and burrs.
Kevlar was inspired by the strengths and flexibility of spiderwebs.
Gecko tape was inspired by the tiny hairs on the feet of the gecko, which allow it to climb around on slippery surfaces.
The ideas for these and hundreds of other incredible products come from nature.
Biomimicry is the art and science of looking at the natural world to solve problems in the built world.
Engineers and industrial designers look to nature for new ideas for these new products and make new ways of making things.
Nature does stuff better than we do. Nature makes things with no waste and no pollution. In nature, waste is always food for something else.
We use high heat and dangerous chemicals to make stuff. Nature makes things using available materials at room temperature.
And nature has been making things, designing systems, and solving problems for billions of years.
So there's a huge catalog of wonderful ideas just waiting to be discovered.
Welcome to the Robotics and Digital Media program at Discovery World. I'm Kirsten.
And I'm Adam. Robotics and Digital Media is a unique, customized experience created by Discovery World for freshman engineering students at UWM.
We are the engineers of the future.
And at UWM, we discover, innovate, and lead.
So, why do we love engineering?
Hi, my name is Kendall, and I love computer science.
Hi, I'm Austin, and I am fascinated with computer engineering.
The first time my uncle showed me those blueprints, I was instantly hooked on just creating things for the world around me.
When I was 12 years old, I read my cousin's thesis on nuclear engineering, and ever since then, I've been really interested in it.
I'm interested in engineering because I've always been fascinated with how things are put together.
My dad has always said, you should be an engineer. And if it wasn't for him, I probably would never have taken any engineering classes.
The reason why I'm studying mechanical engineering is to find alternative fuel sources to make a more eco-friendly sports car.
Engineering isn't just about cold, hard science. It's about passion and ingenuity.
The first thing I ever made was a really simple Java program that basically just tested if it was working, and all it did was print out the words, "Hello World."
One great example of innovative engineering, I think, would be the wheel, because it was one of the first engineering tools made, and it's been around since BC times.
Creativity is an important part of engineering because it's what sets you apart from your peers.
When I was a kid, I loved playing with Lincoln Logs, but I never liked to follow the directions. One of the things I created was, instead of following the directions, I created a giant skyscraper.
I think windmills are a great example of engineering because of the design phase that goes into the blades and making them as aerodynamic as possible, because they have to be able to harness that wind energy.
There's so many things that humans can take away from nature, things that we can't yet mimic, and things that are beyond perfect that we can't yet do.
My name is Sam, and that's why I love engineering.
I'm Kenny, and that's why I love engineering.
And that's why I love engineering.
We recently had a chance to interview Dr. Thomas Consi.
Dr. Consi is a biologist in the Mechanical Engineering Department of UWM's School of Freshwater Sciences.
We talked with him about his work designing robots that explore the underwater world of Lake Michigan.
Welcome, everyone. I'm Sam, this is Kenny. We are inspired engineering students at the University of Wisconsin-Milwaukee.
Our guest is a biologist and engineer with UWM School of Freshwater Sciences.
He designs and builds amphibious robots.
The robots gather data and collect samples from underwater environments like Lake Michigan, and then they find their way home.
It does not get much cooler than that. We are very excited to have him here. Dr. Thomas Consi, welcome. Thank you very much for joining us.
Well, thank you. It's great to be here.
Tell us about LAMAR. What does it do, and how does it do it?
Okay, LAMAR, well, that's an acronym. It stands for Lake Michigan Amphibious Robot. And it's designed to go in the surf zone, which is the region in the near shore where waves break. So it's a very violent region. There's soft substrate like sand, or could even be mud, that's moving around because of the action of waves and currents. So LAMAR is a stout vehicle. It weighs about 250 pounds. It runs on electric motors, which drive 6 wheels, sort of like a little all-terrain vehicle. and it can just plow in with sort of a brute force robot. It just plows into the surf zone and doesn't get pushed around too much. And it can move along a track. It uses GPS for navigation, and we could pre-program it to say, do a lawnmower path, go out, come back, go out, come back, or any other path you the scientist may want. And it could have sensors which could take measurements along that path, or at specific points, geographic points in the water, it could take samples, either water samples or samples of the bottom.
How does Lamar sense the world around it? And how are those sensors inspired by biological sensors?
We're currently working on a set of sensors that will allow the vehicle to detect obstacles in its path. Right now it doesn't have that capability, and that's a very difficult engineering challenge because, well, we're underwater. So most of the obstacle avoidance sensors, as they call them in land robots, won't work. And even some of the marine sensors, like sonar, for instance, is a common obstacle avoidance or obstacle detection sensor. But we're in very shallow water that's full of bubbles from the breaking waves, and that all acts as reflectors, the surface, the bottom, so you can get a lot of spurious signals from sonar. And also we're in water that could be opaque with sediment moving around, so optical sensors could be of limited use. So we've decided to try tactile sensors, touch sensors, and we're actually drawing a lot of inspiration from antenna in, say, lobsters or insects, okay? And antenna have mechanical sensors on them, so they could detect if they have contact with an object, but they're also active sensors in that if you look at an antenna of an insect, if you dissect it, you'll find a lot of muscles at the base. And those muscles enable the antenna to move around, or rather enable the brain of the animal to actively scan around like a blind man and his cane. So you can detect obstacles in a whole sort of cone of detection in front of the animal or the robot. And by manipulating, or rather moving your antenna over the object, you could tell something about its shape. And if you're clever enough and maybe analyze the vibration, if you hit the object with your antenna, you could even tell something about its composition, too.
So, who was your inspiration when you were our age?
I was very much inspired by an article. I remember I was on the train, the Amtrak, going from Boston to New York, and I read this article about gnat robots in a sort of a popular computing magazine. And it was a speculative article about what you could do with robots that were very, very tiny, the size of a gnat, the size of a fruit fly. And this article was by a woman named Anita Flynn, who worked at the Artificial Intelligence Lab at MIT. And since I was there and close by, I made it my business to introduce myself to her, and we had some really nice conversations. And then she, in turn, introduced me to a rather well-known roboticist named Rod Brooks, who told me about this lab that was just forming in underwater robotics, which was a new field. So that leads to advice to you young kids. One is, if you're interested in something, go to where it's happening, and also be bold. You know, if somebody's doing something that's interesting and they're on the campus, you go knock on their door. You know, what the worst they could say is, get out of here. You know, and they probably won't. They'll probably be thrilled that someone took the initiative to go find out about what they do, and that will start opening doors for you, okay? So sort of leap beyond just being in a classroom, you know, not that that's not important, but that is one part of your career development. The other part is making connections and working with people who you find inspiring.
Dr. Consi, thank you for being with us today and sharing your awesome ideas.
Engineers have the tools and knowledge to make the world a better place. We also have the creativity and the inspiration.
And this is very creative and inspiring stuff. For the UWM Innovation House program at Discovery World, I'm Kenny.
And I'm Sam. Good night.
In robotics and digital media experience at Discovery World, we wanted to explore biomimicry and robotics.
But we wanted to do something a little different.
Most biomimetic robots are usually inspired by animals such as spiders, fish, or people.
Plants, however, are some of the most aware and reactive organisms on Earth.
Most of what plants do is invisible to us, unless we're really paying attention. Plants usually move much more slowly than we do.
At least half of what they do takes place underground.
The world is almost entirely different from ours.
Because the plant kingdom is so diverse, there is an incredible amount of room for creativity and inspiration.
So the question we asked ourselves is, what would happen if we designed and built robots inspired by some amazing plants?
Hello, I'm Kenny. I'm studying civil engineering at UW Milwaukee.
And I'm Milo. I'm studying mechanical engineering.
Our experiment was to create a robotic cucumber plant.
Cucumbers are originally from India, but of course they grow all over the world now.
As the cucumber plant grows, it sends out tendrils in search of some kind of support. A tendril will creep along the ground until it touches an object.
After it hits the object, it will change the shape of its cells and curl itself around the object so that it'll drag itself up to another point. To mimic a plant, we tried to mimic each individual component of the plant. So starting with the roots, we used this as sort of ground cover. And then right here, this is the root structure of our plant. Attached to this motor, which connects to the base right here. And this motor spins our tendril on this base around the root structure. So this box right here is the controller for the robot. And what it does is receive signals from the sensors, such as this sensor right here. It also sends out signals to the motors in the robot, such as this motor and also this motor.
The next thing we tried to replicate was the tendril. We did this by having this arm. One of our challenges when creating this robot was to replicate how the tendril moves. We tried replicating it by having a system of rubber bands to try and have this part, the end of the tendril, move faster than the base of the tendril.
Another design challenge that we tried to think through was how to position the motor control unit right here. Initially, we had it sitting off to the side controlling our robot, but that presented problems because the cable would become twisted as the base rotated. So what we wound up doing, as you can see, is positioning this control unit on top of the base so that the cable did not get tangled up into itself. So now, for your viewing pleasure, we'll give you a brief demonstration of our cucumber robot.
As you can see, when the touch sensor finally hits the stick, it'll move around and wrap around the stick. It's very interesting to try and replicate the tendril because it's not like how human hands are, where we have tendons that will grab onto the bone and it wraps. In tendrils, it's the expanding and contracting of cells on the tendril, which is extremely hard to replicate with mechanical materials.
So like Kenny said, this is a tough thing to replicate, and a lot of it's because of the scale, the time scale of which all of this happens. So a cucumber plant is moving maybe a couple revolutions per day. And so what we had to do was use these mechanical components to mimic this biological sort of motion, and that was pretty difficult. So this is pretty great.
Yeah, a lot of fun doing this, man.
I'm Kendall Nelson, and I'm a computer science major.
And I'm Kirsten Labuda, and I'm a mechanical engineering major, and we're students at UWM. Our challenge was to build a robot inspired by the sensitive plant.
The Mimosa pudica is also known as the sensitive plant. It's a fern-like perennial that is native to Central and South America, and it reacts to touch.
This is our robot, which is controlled by the brain, down here. The brain is connected to 3 sensors, here, here, and here. When activated, these sensors make the motors rotate, and the 2 leaves, here and here, will rotate.
How the robot works is when you trip the left sensor, the left side of the leaves will close. Same thing on the right. And if you touch the front sensor, both sides will close, and then 5 seconds after one or both sides closing, it will open back up and reset. Here we go. So the left side, and then 5 seconds later, and then the other side, and then the front sensor. Both sides close.
One of the challenges we faced when making this robot was building the structure. We had to find a way to fit everything together and have the leaves still look like plant leaves. So in the end, we have the 3 sensors mounted on a platform and with the leaves resting on top. This created another problem of weight management. The leaves couldn't be too heavy or they would trigger the touch sensors early. So we had to minimize the components of the leaves.
Designing a robot based on a plant was kind of weird, but fun for us because you don't really think about how plants move. I mean, they grow, but you don't see that ever unless you have a camera on them. So it was really interesting trying to mimic that behavior and see that we could make it react right away, closing up as a result of it being touched. I had a lot of fun.
I had a lot of fun too. This was really cool.
Hello, I'm Adam, and I'm a mechanical engineering student at UWM. I enjoyed exploring robotics and programming. Designing a robot inspired by a plant was cool because I never realized how many components a plant needs to survive and grow. Plant behaviors are really incredible. My partner Ben and I designed and built a robot inspired by the Venus flytrap. The Venus flytrap is native to North and South Carolina. It grows in soil that is poor in nutrients that the plant needs to survive. When the Venus flytrap doesn't get enough nutrients, it eats bugs and spiders. It has trigger hairs that act as touch sensors. When 2 of the trigger hairs are touched within 20 seconds of each other, the trap snaps shut and the plant gets to eat lunch. First, I'd like to show you all the components of my plant robot. First, I have the touch sensors here that act as the trigger hairs. When they're touched within 20 seconds of each other, the robot will slap shut and eat the insect or spider. Next, I have the motors here that each one is connected to a different leaf. When the touch sensors are touched, it will close shut. Next, I have the light sensor here that when there is light, it will have enough nutrients so the robot will not close shut. Then, when there is no light, the robot will activate and close when the touch sensors are touched. And last, I have the brain here that helps make everything work. I had a few challenges while making this robot. One of the challenges I had was the trap would slap shut. It would want to fall over. So I made these legs to help it stand up. A second challenge that I had was the motors. We had them set up to a degree ratio where it would close a certain number of degrees. Well, when it came back, the degrees would be set off and it wouldn't want to close right again. So we changed it and had it set up to the number of rotations it spun and had it set up to 1/4 of a rotation. So when it would close and come back, it would close properly again. So now for the demo. I'll turn my robot on. And I have my insect here that will be eaten. And when there is light, it'll not work. But when there's no light, it shall close and will eat the bug. At Discovery World, we explored robotics, innovations, and digital media production.
We tinkered with new ideas like biomimicry, and we turned those new ideas into something real.
And that's what engineering is all about. That's what building the future is all about.
Discovery World's education and media teams helped us to discover, innovate, and lead.
For the robotics and digital media experience at Discovery World, I'm Adam.
And I'm Kirsten. Remember, it's not just what you know, it's what you do with what you know.